Okay, in this video we're going to look at a ton of group isomorphism examples using a few tools to construct these isomorphisms. And I want to recall a couple of really important ideas before we get into it. So our setup is that we have G1 and G2 are groups, and a map, or otherwise known as a function, from G1 to G2 is called a homomorphism if it respects the group operations. So here, if we apply phi to the product of xy, that's the same thing as taking the product of phi of x and phi of y. And then there are two important subgroups associated with the homomorphism, and the first one is a subgroup of the domain, and in fact it's a normal subgroup. It's called the kernel, and it's everything in the domain that gets sent to the identity in the codomain. And then we have the image, which that is everything in the codomain that is mapped onto by something in the domain. And then furthermore, we have this first isomorphism theorem, which we're going to be using in almost all of the examples, that says that G1 mod the kernel is isomorphic to the image of phi. And then another thing, we don't know that all the time a homomorphism will exist, and in fact we'll see sometimes that homomorphisms won't exist, and we can test that really quickly by noticing that the order of phi of x must divide the order of x, and that's of course if they're both finite. And by the order I mean that's the number of times you have to multiply phi of x to itself to get to the identity, or x to itself to get the identity. So I'm not going to prove this, but I've got this in a previous video that you should probably check out before embarking on this. Okay, so the first example I want to look at is pretty simple. Let's say phi goes from z to zn, and let's say it's defined in the following way. Let's say phi of m is given by the equivalence class defined by m. And so remember, this is going to be all k in z such that k is congruent to m mod n. And we know that equivalence classes form a group under modular addition, if you will. So you add two equivalence classes, and then you can always reduce mod n. Okay, so notice that this is onto, and that's really easy to see because for all m between 0 and n minus 1, we have phi of m equals this equivalence class, right? So we hit everything. And then we also know that, well, it's really easy to check that it's a homomorphism. So notice we take phi of m1 plus m2. Notice that is m1 plus m2, that equivalence class. But by the theory of the group operation of Zn itself, that's the sum of those two equivalence classes, and so that's equal to phi of m1 plus phi of m2. So it's a homomorphism. Now let's check out the kernel. So the kernel of phi is going to be all m in z such that the equivalence class is the same thing as the identity. So it's that. So in other words, it's everything that's a multiple of n, so we can rewrite that as 0 plus minus n plus minus 2n, and so on and so forth, which is often written as the subgroup nz. Now we can apply this first isomorphism theorem to say that z mod nz is isomorphic to zn. Okay, good. So we're done with our first example. Let's move on to the second. Okay, so let's look at our second example. So we're going to take the group Z4 to the group Z2, and how we'll define this is the following way. We'll take the equivalence class defined by M, and I'll put a 4 there to say that we're working like mod 4, and we're just going to send that to the equivalence class defined by M and mod 2. So in this case, we need to check that this thing is well defined, because here we're looking at things that might have like more than one value over on the left hand side, and I don't mean more than one value but more than one name for the same element. So let's go ahead and suppose that M1 4 is the same thing as M2 4. Okay, great. But now notice that means that M1 minus M2 4 is the same thing as the equivalence class of 0 mod 4. But what that tells us is that M1 minus M2 is congruent to 0 mod 4. But anything that's congruent to 0 mod 4 is a multiple of 4. But what that tells us is that it's also a multiple of 2. Obviously, a multiple of 4 is also a multiple of 2. So we can say that M1 minus M2 is also 0 mod 2. So let's reiterate. This means that M1 minus M2 is a multiple of 4, but it follows that M1 minus M2 is a multiple of 2. But what that tells us is that M1 minus M2 equivalence class mod 2 is the same thing as the equivalence class of 0 mod 2. But finally, that means that the equivalence class of M1 mod 2 is the same thing as the equivalence class of M2 mod 2, but one of these is phi of M1 and the other one is phi of M2. So we're good to go. So it is a well-defined map. Okay, so now let's go ahead and check that it is a homomorphism. It's actually going to follow in a very similar way to this here. So if we do phi of M1 4 plus M2 4, that's going to be the same thing as phi of M1 plus M2 4. But by our map, that's defined to be M1 plus M2 2. But that's going to be equal to M1 2 plus M2 2, but that's going to be phi of M1 4 plus phi of M2 4. So it is in fact a homomorphism. And then it's also surjective. Notice we only have to hit 2 elements. We only have to hit the element 0 and 1. And notice that phi of the equivalence class of 0 is going to be the equivalence class of 0. And phi of the equivalence class of 1 is going to be the equivalence class of 1. So it is surjective. Okay, I'll clean up the board and then we'll calculate the kernel and then we'll apply the first isomorphism theorem. Okay, so now we're ready to calculate the kernel. So let's see, the kernel of phi. So this is going to be all M4 in Z4 such that, M sub 4 like that, such that when you apply phi to this, you get the identity. In other words, the equivalence class of M is the same thing as the equivalence class of the identity, which is 0 in this case. And now let's just reiterate that this is phi evaluated on the equivalence class from the domain. So we are really taking the kernel here. Okay, but now it's not too hard to see that we can just list the elements in the kernel in this case. So notice we have the number 0 is in the kernel. And then number 1 is not, because that gets mapped to the equivalence class of 1. The number 2 is in the kernel because that gets mapped to the equivalence class of 2. But if we're working mod 2, that's equal to 0. The equivalence class of 3 is going to be mapped to the equivalence class of 1. So in fact, we're all done here. So it's just 0 and 2. But now, notice, if we wanted to, we could write this a couple of different ways. We could say that this is the cyclic subgroup generated by that equivalence class defined by 2. We could also say that this is equal to 2Z4. Okay? But now, applying the first isomorphism theorem, we see that Z4 mod 2Z4 is in fact isomorphic to Z2, or we could write that with this other notation as Z4 mod, the cyclic subgroup generated by this equivalence class, is isomorphic to Z2. Okay, good. So I'll clean up the board and then we'll get on to our next example. Okay, so for our next example, we're going to look for a homomorphism from Z6 to Z15. So in this case, we have to figure out what the homomorphism should be in the first place, and we have to use this fact down here that the order of the image of an element must divide the order of the element. So let's first notice that orders of elements of Z15 are only two possibilities. Well, I should say three possibilities. You could have something of order 1. And now let's go ahead and list the elements of order 1. So we have the identity, which is 0, the equivalence class of 0, I should say. And then we also have elements of order 3. So how many of those do we have? Well, let's see. We have 5, so that has order 3, and then I believe 10, that is also going to have order 3. So notice 5 plus 5 is 10, 5 plus 5 plus 5 is 15, which is the same thing as 0. 10 plus 10 is 20, which is the same thing as 5, and 10 plus 10 plus 10 is 30, which is the same thing as 0. So those are the elements of order 3, and then we have some elements of order 5 as well. So let's see, what are our elements of order 5? So we'll have 3 is going to have order 5, 6 is going to have order 5, 9 is going to have order 5, and then finally 12 is going to have order 5. Okay, great. Now I should say that really quickly we can calculate the order of an element with this following formula. So the order of m in Zn, so we could write it like that. So that is going to be equal to n over the GCD of m and n. So again, that's in another video that we did previously regarding cyclic groups, and since this is a cyclic group, we're good to go here. Okay, so notice there's one more possibility for orders, and that's 15. So remember, the order of an element has to divide the order of our group, and these are the only divisors of 15. And I'm just going to put here that the rest of the elements are going to have order 15. And notice that's everything that's relatively prime to 15. Okay. So now we need to figure out what we can do with this homomorphism, but it's going to be completely determined by where we send the number 1. Now, using this rule over here, we see that the order of where we send 1 needs to divide the order of 1 in the domain. But now notice the order of 1 in the domain is equal to 6. So what that tells us is that the order of phi of 1 needs to be equal to 1, 2, 3, or 6. Okay, so now let's see what we've done here. Over here we see that all the possible orders of elements in the codomain are 1, 3, 5, and 15. And then the order of the image of our generator needs to be 1, 2, 3, or 6. So what that tells us is that it's impossible to have an order 6 image of the number 1, and that's because 6 doesn't exist over here. It's impossible to have order 2, so all we have are the possibilities 3 and 1. And so now let's look at this one first. If we have order 1, so that means, well, let's write this out. So case number 1, and that would be the order of phi of 1 is equal to 1. So that means that phi of 1 is going to be equal to 0. And I should say 0 in Z15, which we can write like that. But what that tells us is that the kernel of phi is everything. So it's all of Z6. And the image of phi is equal to only the identity. So this is pretty boring. What we ended up with here is that Z6 mod Z6 is equal to the trivial group that is lying within Z15. So there's nothing really going on there. So let me clean up this bit, and then we'll look at the more interesting cases. Okay, so now we're ready to look at the second case of this homomorphism from Z6 to Z15, and that's the case when phi evaluated at this equivalence class of 1 mod 6 has order 3. And so notice from our previous chart that we had, that told us that this element has to be sent to either 5 or 10. It's similar whether or not we send it to 5 or 10. It's about the same sort of calculation. So I'll just assume that our map is defined by phi of 1 mod 6 goes to 5 mod 15. So that equivalence class. Okay, great. So from here, we can make a chart of what happens to every element of Z6. And so that's nice to do because we only have 6 elements, so it's not too bad. So notice 0, the equivalence class of 0 is going to go to the equivalence class of 0 on this side. The equivalence class of 1 is going to go to the equivalence class of 5 on that side, like we had decided. The equivalence class of 2 is going to go to the equivalence class of 10 on this side because we're requiring it to be a homomorphism. And then the equivalence class of 3 is going to go to the equivalence class of 15. But notice that 15 is the same thing as 0 mod 15. Good. The equivalence class of 4 is going to go to the equivalence class of 20, but 20 is the same thing as 5 mod 15. The equivalence class of 5 is going to go to the equivalence class of 25, but 25 is the same thing as 10 mod 15. Okay, so now that we've got that, we can easily see what the kernel and the image of this homomorphism are. So notice that the kernel of phi is made up of 2 elements, the equivalence class of 0 and the equivalence class of 3. Okay, good. But now notice that that is equal to the cyclic subgroup generated by the equivalence class of 3 under like modular addition. But for what it's worth, that's isomorphic to the group Z2 because it's a cyclic group of order 2, and all cyclic groups are isomorphic if they have the same order. And now notice that the image of phi is given by the following. We only hit the elements 0, 5, and 10. So we can write that down. So 0, 5, and 10. But notice that is the cyclic subgroup generated by the equivalence class of 5, which for what it's worth, that is isomorphic to Z3 as well. Or sorry, Z3 because it has order 3. Okay, good. Now we can apply the first isomorphism theorem to say that Z6 mod, this cyclic subgroup generated by 3, is going to be isomorphic to the cyclic subgroup inside of Z15 generated by 5, which it itself is isomorphic to Z3. Okay, good. So I'm going to go ahead and clean up the board, and then we're going to do some more examples. Okay, now I'm going to do several examples involving the dihedral group. So let's just recall that it's generated by rotation R, reflection S. We have R to the n is the same thing as S squared, which is the identity, and these generators do not commute. R times S is the same thing as S times R to the n minus 1. Now when you're deciding whether or not some map to or from the dihedral group is a homomorphism, all you need to check is that these defining relations are satisfied on both sides of the map. And so that's exactly how we'll do this. Okay, great. So let's look at this first one defined in the following way. So let's define it by dn gets sent to Z2, and we're taking R to 0. So I'll stop writing the equivalence class mod 2 because now we're just working with Z2 and we're not working with like competing Zn, so it's not as confusing. So we'll take R to 0 and we'll take S to 1. Okay, so let's go ahead and check that these 3 defining relations are satisfied. So notice we have phi of Rn. So on the one hand, that should be equal to 0, but on the other hand, that should be equal to 0 plus 0. So yeah, we're good to go. This thing is satisfied. Okay, good. Now let's look at phi of s squared. So on the one hand, that's the same thing as phi of e, which should be 0. But then on the other hand, that should be equal to phi of s plus phi of s, which is equal to 1 plus 1, which is 0. So yeah, it checks out. So as long as I'm getting a true statement there, this checks out and it is in fact a homomorphism. Okay, good. So we've got one more thing to check. And let's go ahead and check this, that phi of rs, that should be equal to phi of sr to the n minus 1. Okay, so now that should be equal to phi of r plus phi of s, which is equal to 0 plus 1, which is 1. Okay, but on this side, that should be equal to phi of s plus n times phi of r, which is again 1 plus 0, which is 1. So again, it's satisfied in this case. Okay, good. So now let's go ahead and notice that our image is all of Z2. So in other words, this thing is surjective. That's easy to see. I mean, we see both elements being mapped onto right here. So I can add another part of the arrow there to say it's surjective. And then the kernel is also easy to see. So notice the kernel of this thing is equal to the cyclic subgroup generated by R. Okay? So again, that's easy to check. Notice we have phi of r to the k is going to be equal to k times phi of r, which is k times 0, which is 0. Okay, good. But then any reflection, like phi of s times r to the k, is going to be phi of s plus k times phi of r, which is 1. So any reflection is sent to 1, any rotation is sent to 0. Okay, good. But now, notice that that tells us that this dihedral group Dn mod the kernel, which is the cyclic subgroup which is generated by R, is isomorphic to Z2. Okay, good. So I'll clean up the board and then we'll do another one. Okay, so being inspired by our last example, we would like to do a new example in the following way. Dn to Zn, where we send R to 1 and we send S to 0. So we need to check that that's a homomorphism. We'll actually see it's not a homomorphism, but it seems like kind of it should be a homomorphism given that it is so in parallel to our last example. Our last example where we're sending every rotation to the identity, and now we're sending our reflection generator to the identity. But let's just see what goes wrong here. So notice if we take phi of rs, so defining this to be a homomorphism, this is going to be equal to phi of r plus phi of s, which is equal to 1 plus 0, which is 1. Good. But then notice if we do phi of s times r to the n minus 1, notice that that is going to be equal to phi of s plus n minus 1 times phi of r, which is equal to n minus 1. Okay, good. But now notice that these are not equal, and that is because 1 is not congruent to n minus 1 mod n unless n equals 2. Okay, so there's a special case if we have D2 to Z2, this is going to work, but otherwise this is not going to work. So we can't have a similar example to the one that we just had before. Okay, good. I'll clean up the board and then we'll do another one. Okay, so for our next example, we'll look at D2n. So here we have an n-gon with an even number of vertices, so 2n vertices, I should say. And in this case, what we'll do is we will take R to 1 and we'll take S to 0. And we'll see that this is going to work in this case, even though something similar didn't work in the other case because we restricted it quite a bit. We put Z2 over here and we have D2n instead of just Dn over here. Okay, so let's go ahead and check that these defining rules are satisfied, but now notice we need a 2n here and a 2n here. So let's go ahead and add that in, 2n, and then we have a 2n here. Okay, good. So now notice that we have phi of r to the 2n. So on the one hand, that should be equal to phi of the identity, which is equal to 0. But then on the other hand, that should be equal to 2n times phi of r, which is equal to 2n. But now notice in Z2, 2n is equal to 0, so we're okay there. Okay, good. Now, let's see what happens to phi of s. So I won't even check this because s squared is equal to the identity, but it's already being sent to the identity. And so all we need to do here is like 0 plus 0 is equal to 0. So now let's check this rule over here. So let's do phi of rs. So if this is a homomorphism, then that should be phi of r plus phi of s. Okay? But now notice that's equal to 1 plus 0, which is 1. But now let's do phi of sr to the 2n minus 1. Okay, so if this is a homomorphism, this should be phi of s plus 2n minus 1 times phi of r, which is equal to 2n minus 1, which is equal to negative 1, which is equal to 1 if we're working in Z2. So in Z2, 1 is equal to negative 1, so we're okay. So yes, these two are equal. So now since we've checked the defining relations hold on both sides of the map, that means that in fact this is a homomorphism. Another thing we can notice is that it is obviously surjective because we're hitting both elements here. So we have a double arrow there, it's an onto homomorphism. Okay, I'll clean up this bit of the board, we'll calculate the kernel, and then we'll look at an isomorphism that is derived out of that kernel. Okay, so now let's go ahead and calculate the kernel. So the kernel of phi, so it's pretty easy to see that it contains the following elements. So it's going to contain the identity, it's going to contain r squared. So it's obviously going to contain r squared because r squared will be sent to 1 plus 1, which is 0. It'll contain r to the 4th all the way up to r to the 2n minus 2. Okay, good. And then notice it's also going to contain every reflection. So it's going to contain S, it will contain, sorry, not every reflection, but every reflection of this form. So it'll contain S, SR squared, SR to the 4th, all the way up to SR to the 2n minus 2. But now notice that that is going to be a subgroup of D2n, which is generated by S and then R squared. Okay, good. But now, notice that S and R squared satisfy the following rules. So S, R squared satisfy these rules. S squared equals R squared to the nth power, which equals the identity. And then, finally, from this, we could say R squared S equals SR squared to the n minus 1. But notice those are exactly the defining rules of the dihedral group Dn. So this is isomorphic to Dn. Okay, good. So we've got a copy of Dn inside of D2n, which happens to be the kernel of this homomorphism. Okay, good. So from this, we can see that D2n mod this kernel is isomorphic to Z2. And you can think about this kernel any way you want to. You can think about it as being generated by those two elements. You can think of it as a copy of Dn living inside D2n. Okay, good. I'll clean up the board and then we'll move on. Okay, so for our next example, we'll look at the map from D6, so the dihedral group of order 6, the symmetries of the hexagon, to S6, all bijections from 1 to 6 to 1 to 6. We'll take R to be this 6 cycle, 1, 2, 3, 4, 5, 6. We'll take S to be this product of 3 disjoint 2 cycles, 1, 6, 2, 5, and 3, 4. And to see the inspiration for this, let's notice that if we take a hexagon and we label it in the following way, 1, 2, 3, 4, 5, 6. Notice that this rotation is obviously 1 click clockwise. That would be that sort of a map. And then this reflection is given by a reflection about this axis, and that's what's happening to the vertices. Okay, and in fact, there is a map like this that will take Dn to Sn, which I'll let you guys think about that. Okay, so now let's check that this is a homomorphism. So let's check the defining relation for the rotation. So phi of r to the 6, so that is equal to 1, 2, 3, 4, 5, 6 to the 6th power. In other words, it composed with itself 6 times, but that's obviously going to get us to the identity, which is the same thing as phi of the identity, which is exactly what we should get here. Okay, and then I'll let you guys check the same thing for the reflection. Obviously, if you get s squared on this side, you get the identity. If you combine this with itself one time, you get the identity. So the next thing we need to check is the way that the R and S interact with each other. So let's calculate phi of RS. So notice that's going to be 1, 2, 3, 4, 5, 6 with 1, 6, 2, 5, 3, 4. So if it's a homomorphism, that rule will be satisfied, but let's see what that is. So that is going to be, let's start with 1. Notice 1 is sent to 6, and then 6 is sent back to 1. So notice we can close that off. And now let's see what happens to 2. So notice 2 is sent to 5, and then 5 is sent to 6. So let's see, that means 2 goes to 6. And now let's see where 6 is sent. 6 is sent to 1, 1 is sent to 2, so that closes this thing off. We just get 2, 6. Okay? So now the next number we need to check is 3. So 3 is sent to 4, 4 is sent to 5, so that means 3 is sent to 5. Okay? Now 5 is sent to 2, 2 is sent to 3, so we can close that thing off. Okay, so now notice we've accounted for the numbers 1, 2, 3, 5, and 6. We haven't accounted for the number 4, but notice that will be fixed because 4 is sent to 3 and then 3 is sent to 4, so 4 is fixed. So now notice that this is really just the product of the 2 cycles, 2, 6, and 3, 5. Okay, good. Now let's compare that to phi of SR to the n-1, which is going to be to the 5 in this case. So notice that is going to be 1, 6, 2, 5, 3, 4. So that's our S component. And then now notice that R to the 5th we can get very, very quickly just by counting by 5s. So notice we'll have 1, 2, so we'll go 1 to 6, 1 to 6, and then to 5, and then to 4, and then to 3, and then to 2. Okay, and that's just counting by steps of 5. So instead of going 1 to 2, we'll go to 1, 1, 2, 3, 4, 5. So we go 1 to 6. And then starting at 6, we'll go 1, 2, 3, 4, 5. So that goes to 5. And then starting at 5, we'll go 1, 2, 3, 4, 5. So that goes to 4. Okay, great. Now, let's check that this is the same thing as what we got up there. So let's see where 1 is sent. So 1 is sent to 6 here, back to 1 there, so we can close that up. Now let's do 2. So here, 2 is sent to 1, 1 is sent to 6, so 2 is sent to 6. Let's see what happens to 3. So 3 is sent to 2, 2 is sent to 5, so that means 3 is sent to 5, and then we can argue that 4 is going to be sent to itself, so 2, 6, 3, 5, so that means that these are equal, so that makes this thing a homomorphism. Okay, so now that we know that it's a homomorphism, we can look for the kernel and the image. So I think it's maybe just easiest to write the image in the following way. So this is going to be everything generated by the 6 cycle, 1, 2, 3, 4, 5, 6, and then 1, 6, 2, 5, 3, 4. You could definitely write out all of those elements, but I think it's easiest just to write it like that. Okay, so now let's look for the kernel. I'm going to claim that the kernel of this is only the identity. And let's see why we can claim that. So first of all, notice that the order of R equals 6, and the order of 1, 2, 3, 4, 5, 6 is also equal to 6. And so since an element of order 6 is being sent to an element of order 6, that tells us that phi of R, let's write it like this, to the n is not equal to the identity if n is equal to 1, 2, 3, 4, 5, because that would contradict the fact that this has order 6. Okay, but then next, it's easy to check that none of the reflections are sent to the identity either. So from there, we can see that the kernel is only the identity element E, which tells us that in fact we have an isomorphism. D6 is isomorphic to the image of phi because we don't have to mod out by another kernel in this case. All right, I'll clean up the board and then we'll do some more. Okay, so for our next one, we're going to take a classic map from Sn to Z2 defined in the following way. So let's say phi of sigma from Sn equals 0 if sigma is even, and then let's say it's 1 if sigma is odd. Okay, good. So it's actually pretty easy to check that this is an isomorphism. Sorry, that this is a homomorphism because of how the evenness and oddness is defined. Remember, that's defined by sigma can be written as an even number of transpositions or an odd number of transpositions. So now notice that this thing is obviously onto because the identity is sent to 0, but for instance, the permutation 1, 2 is going to be sent to 1. So that means we can achieve both elements of Z2 very, very easily. Another thing we notice is that the kernel of phi is going to be all sigma in Sn, where sigma is even, but we have a name for that. That's equal to An, the alternating group. Okay, so what this tells us is that Sn mod An is isomorphic to Z2. Okay, great. So I'll clean up the board and then we'll keep going. Okay, so for our next one, we'll take phi going from GL to R. So remember, that's all 2x2 matrices with non-zero determinant. So our group operation here is just matrix multiplication. And then we're going to take this to the multiplicative group of non-zero real numbers. And here our homomorphism will be defined by taking the determinant. So, by linear algebra, we know that the determinant of a product AB is equal to the determinant of A times the determinant of B, so that in fact makes this a homomorphism. Okay, great. And then the kernel here, so the kernel, so that's going to be all A in GL2R, such that phi of A, which is equal to the determinant of A, is equal to 1, because that's the identity over there in the multiplicative group of non-zero real numbers. But there's a name for this. This is called SL2R. Great. But now we can apply the first isomorphism theorem to see that GL2R mod SL2R is exactly isomorphic to this multiplicative group of non-zero real numbers. Okay, good. So we'll keep going. Okay, so for the next couple of examples, we're going to look at these objects, little GL2R and little SL2R. So these are in fact Lie algebras, but we're just going to be exploiting their existence as groups where our operation is matrix addition, not matrix multiplication. So GL2R is just all 2 by 2 matrices. So obviously that forms a vector space, and every vector space is a group under addition. And then SL2R is a subspace, also a subgroup, which is given by all elements from this group, so all 2 by 2 matrices where the trace is equal to 0. The trace is the sum of the elements on the diagonal. Okay, so now the first thing I want to look at is this map from GL2R just to R. So now addition is my operation on both sides, and what I'll do is I'll take phi of A to be equal to the trace of A. Okay, so we can easily check that this is a homomorphism. So notice if we have phi of A, B, C, D plus X, Y, Z, W, that is going to be clearly equal to A plus D plus X plus W, which is equal to phi of A, B, C, D plus phi of X, Y, Z, W. Okay, good. So clearly a homomorphism. So now notice that the kernel of phi is going to be everything that has trace 0. So in other words, this is going to be all matrices A, B, C, negative A, such that A, B, and C are real numbers. So it's easy to see that those are going to be all the matrices that have trace 0. So if we're adding along the diagonal, it means this element and this element have to be negatives of each other. Okay, good. So, but notice that this is equal to this thing that we defined to be SL2R up there. Okay, so now what we see is that this GL2R mod, this SL2R, is the additive group of real numbers, and we get that by the first isomorphism theorem. Okay, good. I'll clean up the board and we'll look at a related example. Okay, so for our next example, we'll look at phi from GL2R to SL2R given by the following. Let's say phi of A, B, C, D is equal to A minus D, B, C, D minus A. Okay, so notice that definitely lands inside of SL2R. So now let's go ahead and look for the kernel of this. So the kernel of phi, so that's going to be all A, B, C, D, such that phi of A, B, C, D, which is equal to A minus D, B, C, D minus A, is equal to the 0 matrix. Good. But if that's equal to the 0 matrix, that means B and C have to be 0, and that means A and D have to be equal to each other, because we want A minus D to be equal to 0. So that's going to be everything of this form, A, 0, 0, A, where A is some real number. Okay, good. But now notice that's a copy of the additive group of real numbers living inside of GL2R. So what that tells us is that if we take this GL2R and we mod out by this kernel, which is the additive group of real numbers, we get this SL2R. Okay, good. So we'll keep going. Okay, so for our next example, we'll look at the following. So let's take a map from Z to the multiplicative group of non-zero real numbers. So there are 3 interesting choices here. So choice number 1 is we can take phi of 1 to 1. And so what that tells us is that phi of n is equal to 1 to the n, because we're doing this multiplicatively. But that means that the kernel of phi is equal to all of the integers, because we're only mapping onto the identity, and the image of phi is just equal to the number 1. So what we have here is that z mod the kernel, which is all of z, is isomorphic to this trivial group within the multiplicative group of non-zero real numbers. Okay, so that's one possibility. The next possibility is we could take phi of 1 to negative 1, which notice that's the same thing as saying phi of n equals negative 1 to the n. Okay, but now notice the kernel of phi, so that's going to be all real numbers. Sorry, so that's going to be all integers such that negative 1 to that integer is equal to 1. In other words, that's going to be all even integers. So 0 plus minus 2 plus minus 4 and so on and so forth. That's how you can get negative 1 to the n to be positive 1, obviously. So again, we generally call this 2z, and then applying the first isomorphism theorem, we see that z mod 2z is isomorphic to this group made up of 1 and negative 1 within the group of non-zero real numbers under multiplication. Okay, now the next interesting example is what if we take phi of 1 to a, in other words, phi of n equals a to the n, where a is in this group, but it's not equal to 1 or negative 1. Okay? So it's easy to check in this case that the kernel of phi is only equal to 0. So notice if we take a to the 0, we're going to get 1, so that'll be the kernel, but nothing else will be in the kernel because no other number in the real numbers, when you raise it to some power, do you ever get back to the identity, in other words, the number 1. So what this tells us is that z itself is isomorphic to this group made up by a to the n, where n is in z, as a subgroup of the non-zero group of real numbers under multiplication. Okay, so we've got some more to do. Okay, so now let's look at a related example. We'll take phi going from R, so that additive group of real numbers, to R plus times, so in other words, the multiplicative group of positive real numbers. And let's take that map to be phi of x is equal to 2 to the x. So now, first of all, we'll notice that the kernel of phi, so that's going to be all real numbers x, such that 2 to the x equals 1. Okay, good, but notice that that is just going to be 0. That's the only thing that when you raise 2 to that power, you get the number 1. And then let's also notice that this thing is onto, the image is all positive real numbers. And how we can see that is we can let y be a positive real number. And then maybe we'll set x equal to the log base 2 of y. And then notice that phi of this value of x is going to be 2 to the log base 2 of y, which is y, so that means this thing is onto. So what that tells us is that the additive group of real numbers is isomorphic to the multiplicative group of positive real numbers. So notice it may not be, well, we did not prove that it's isomorphic to the whole group of non-zero real numbers under multiplication, but just the positive ones. Okay, good. So I'll clean up the board and then we'll do some more. Okay, so now let's define phi from z into c, and let's say phi of n equals I to the n. Okay, great. But now notice that the image of this is going to be equal to 1 I minus 1 and minus I, but that's it. So we have I to the 0, I to the 1, I squared, I cubed, but now notice I to the 4th is back to 1 because I to the 4th power is equal to 1. Okay, great. And then notice the kernel of phi, so that's going to be all in the integers such that I to the n is equal to the number 1. So that's equal to all multiples of 4. So that's easy to check. So notice that what we get out of this is that Z mod 4Z, in other words, the domain mod the kernel, is isomorphic to this cyclic subgroup generated by I, which is equal to the image of phi, and that's inside this multiplicative group of non-zero complex numbers. Okay, good. So we're going to do a related example of this now. Okay, so as a related example, let's say we have phi going from Z to the multiplicative group of non-zero complex numbers in the following way. Let's say that phi of m is equal to e to the 2 pi I m over n. But now notice that the kernel of phi, so that's going to be all m such that e to the 2 pi I m over n equals the number 1. But now using Euler's formula, that means that cosine of 2 pi m over n needs to be equal to 1, and sine of 2 pi m over n needs to be equal to 0. But it follows, then that means that n must divide m. Okay, great. But what that tells us is that this kernel is exactly equal to all multiples of n. So if n divides m, then that means that m is a multiple of n. So we could say m is equal to nk. But what that tells us is that z mod nz is isomorphic to a subgroup of the non-zero group of complex numbers generated by this. So notice we could write this in the following way, so that this is equal to 1 omega n all the way up to omega n minus 1. In other words, the cyclic subgroup generated by omega n, which is isomorphic to Zn, which is inside of this group of non-zero complex numbers, where we're letting omega n be e to the 2 pi I by n. So we'll do one more example. We'll do a couple more examples where we have complex numbers on the right-hand side. Okay, so for our next example, let's take phi going from z to the complex numbers, and let's say that phi of n is equal to 2 to the n, I to the n. In other words, this is 2I to the n. Okay, good. And so now it's easy to check here that the kernel of phi is going to be equal to only 0. Because what we need is we want 2I to the n to be equal to 0, but to be equal to 1, but the only way for that to be the case is n equals 0. But now notice that the image of phi, well, it's maybe not super interesting to write, but it can be just written in this form. So all powers of 2I to the n. Maybe the interesting thing to notice is that we can graph this in the complex plane in the following way. So notice 2I to the 0 is equal to the number 1. 2I to the 1 is equal to 2I. 2I squared is equal to negative 4, like that. 2I cubed is going to be equal to 1, 2, 3, 4, 5, 6, 7, 8 is going to be equal to negative 8I. And so what we're forming here is some sort of spiral. Notice that 2I to the negative 1 is going to be back here at a half, and then it's going to spiral in like that. So what we've done is we've, in a sense, put the integers into this spiral in the complex plane. Okay, good. So we'll do some more. Okay, so now the one we want to look at is this map from the additive group of real numbers to the multiplicative group of non-zero complex numbers, where we take phi of x to be e to the 2 pi I times x. Okay, great. So now it's easy to see that the image of this is going to be equal to all z in the non-zero complex numbers, such that the modulus of z is equal to 1. Okay, and why is that? Well, if you have the modulus of z is equal to 1, it means that z is on the unit circle. But if z is on the unit circle, it can be parametrized by cosine theta, comma sine theta. But then in the complex plane, that's exactly equal to cosine theta plus I sine theta. But that's exactly what this map is doing. Okay, great. So in other words, we get the whole unit circle here, which is sometimes called the circle group, which is denoted by this T, and it's sometimes called like S1. Okay, great. Now let's look at the kernel. So the kernel of phi, that's going to be all real numbers x, such that e to the 2 pi I x equals the identity over on the right hand side, which is the number 1. But what that tells us, using Euler's formula, is that cosine 2 pi x needs to be equal to 1, and sine 2 pi x needs to be equal to 0. Okay? Good, but what that tells us is that x is going to be an integer. Notice all integers are going to satisfy this, but everything that's not an integer will not satisfy this. Notice if x is a half integer, we'll get that sine of 2 pi x is equal to 0, but we'll get cosine of 2 pi x equals negative 1. So we need x to be an integer in order to satisfy both of these equations. So what that tells us is that this kernel is equal to the integers inside of the real numbers. And so what this gives us is that the real numbers mod the integers is isomorphic to the circle group S1. Okay, and now how you want to think about this is you have this number line, which you can put all of the integers on this number line, and then you identify all of the integers as being the same point, which wraps this number line around into a circle. That's how you kind of want to think about this. So notice this interval right here is going to be wrapped into the circle, this interval right here gets wrapped into the circle, and so on and so forth. Okay, I'll clean up the board and then we'll keep going. Okay, so now let's look at a map from the Quaternions. So recall that the Quaternions are made up of all the numbers plus minus 1, plus minus I, plus minus j, and plus minus k. And we have rules like I squared equals j squared equals k squared equals negative 1. I times j equals k. J times I equals negative k. Let's see. J times k equals I. K times j equals negative I. K times I equals j, and finally I times k equals negative j. So there's like a way to think about this as putting I, j, and k on a circle, and there's some sort of way to remember this, but I'll just write this down. Okay, good. Now what we want to do is define a map from Q8 into Z2 cross Z2 by the following. So let's go ahead and say that I gets sent to 1, 0, J gets sent to 0, 1, and then K is going to be sent to 1, 1. Okay? Good. And so now, using that over there, we can see that this indeed does define a homomorphism. And really what saves us here is that 1 is the same thing as negative 1. In other words, 1 is the same thing as its inverse. So I and negative I are going to be sent to the same thing. Okay? And now notice that this tells us that negative 1 is going to be sent to 0, 0. Okay, good. Now, notice that this thing is onto. We can see that because we've achieved everything except the identity, but 1 is sent to the identity and negative 1 is also sent to the identity. And I should say that we can list what happens to everything now. So 1 and negative 1 are sent to the identity, I and negative I are sent there, j and negative j are sent there, and k and negative k are sent there. And then it's easy to check that this makes a homomorphism. So notice that thing's onto, but then the kernel of phi is going to be equal to just the subgroup 1, -1, which is the cyclic subgroup generated by -1, which tells us that Q8 mod the cyclic subgroup generated by -1 is isomorphic to Z2 cross Z2. Okay, so for our next example, we're going to look at the group U15. In other words, everything relatively prime to 15 with operation multiplication mod 15. So notice here we get 1, 2, 4. We can't have 5 or 6. We get 7 and 8. We can't have 9 or 10. We get 11, no 12. We get 13 and 14. So notice there are 1, 2, 3, 4, 5, 6, 7, 8 elements. So we know that there are only 3 groups that are abelian of order 8. There's Z2 cross Z2 cross Z2, Z2 cross Z4, and Z8. So this must be one of those, and we'll construct the isomorphism. And we'll do that by looking for some cyclic subgroups. So let's first of all notice that the cyclic subgroup generated by 2 is going to be equal to 1, 2, 2 squared, which is 4, 2 cubed, which is 8, and then 2 to the 4th power is going to be 16, but 16 is 1 mod 15. So we get that. So notice that's isomorphic to Z4. So in other words, we have a subgroup of this that is isomorphic to Z4. Now, notice built into this, we see that the cyclic subgroup generated by 4 is just 1 and 4. Okay, good. Now let's look at the cyclic subgroup generated by 7. So here we get this is 1, 7. 7 times 7, which is 49, but 49 is 4 mod 15. So this is 4. And then 7 cubed is going to be the same thing as 7 times 4, because 4 is 7 squared, so that's going to be 28. But 28 is -2, which is 13 mod 15. So we get that. So notice that this cyclic subgroup 4 is inside the cyclic subgroup 2 and the cyclic subgroup generated by 7. So that's interesting. And then notice that the cyclic subgroup generated by 11 is just 1 and 11. But now notice we can get the rest of the elements by combining things from 2 and 11. So notice if we do 2 times 11, we get 22. So 2 times 11 is 22, which is the same thing as 7 mod 15. Good. If we do 4 times 11, we're going to get 44, which is -1, which is 14 mod 15. Good. And then finally, if we do maybe 8 times 11, we're going to get 88, which you can check that that is equal to 13 mod 18. Okay, good. So now that should motivate the following map. So let's take this map from Z cross Z into U15. And let's say it's given in the following way. We'll take M comma N and we'll send it to 2 to the M times 11 to the N. Okay, so from everything that we've done above, we see that this thing is definitely onto. And then also, we can see that it's a homomorphism, so you can check that it's a homomorphism. It's not too bad. And then the kernel of this is going to be all values when M is a multiple of 4, because notice 2 to the 4 is equal to 1, and then when N is a multiple of 2, so this is equal to 4Z cross 2Z. Okay? So what that tells us is that Z cross Z mod 4Z cross 2Z is isomorphic to U15, but it's pretty clear that this is Z mod 4Z cross Z mod 2Z. In other words, Z4 cross Z2 is isomorphic to U15.